Good evening. So today I am going to discuss three theorems from probability for senior intermediate board of examination. So the first one is the addition theorem on probability, second one is conditional probability and multiplication theorem. Third one is Bayes theorem. So for the addition theorem, to prove that addition theorem, we need some reminders. Those are if A and comma B are mutually disjoint or disjoint events or exclusive events, then probability of A union B is equal to P of A plus P of B. Okay. Second one is that if A is subset of B, then probability of A B minus A is equal to probability of B minus probability of A. Okay. These are the things need to be remembered now. Now we know that third one, if probability of empty set is equal to impossible event. Now let us go for the theorem, addition theorem. The statement is if A and B are any two events in a sample space of a random experiment, then P of A union B is equal to P of A plus P of B minus P of A intersection B. It has two cases. The proof has two cases. First case is that suppose this is the sample space. A is an event and B is an event. Clearly A and B has no common points. First point is case 1, when A intersection B is equal to empty. That is mutually exclusive events. So by axiom of additivity, that implies that probability of A intersection B is equal to, as I told, that probability of empty set. Probability of empty set is 0, right? When two sets are disjoint, then what is axiom of additivity? Axiom of additivity says that by axiom of additivity, what we have is probability of A union B is equal to probability of A plus probability of B. So this can be written as probability of A plus probability of B minus 0. Probability of A plus probability of B minus 0. Instead of 0 we can write probability of A union B. Therefore it is the theorem. Therefore in this case probability of A union B is equal to P of A plus P of B minus P of A intersection B. Case 2 is when A intersection B is empty, not equal to empty. When A intersection B is not empty, let it be A and this one be B. This is A intersection B, right? This yellow part is B minus A. This part is called subtracting B from A minus B. So this is as usual A intersection B, right? Suppose this case A intersection B not equal to empty, so some intersection is there. So this is A intersection B, right? This is A intersection B. Once observe that in this one, what our theorem says that A union B, right? So we need A union B. A union B is equal to, A union B means a complete thing. A union B minus A. So what is B minus A? B minus A is this yellow part, right? If we add A, we will get A union B only. Understood, right? Understood. A union B minus A. Wait, if you don't understand that, I will tell that. This is B, right? This is A, right? B minus A mean that subtracting A from B, right? We get only this point because A is subtracted, right? A is subtracted. What happens if you subtract A intersection B from A? A intersection B from A or B intersection from B. If A intersection B is subtracted, so B minus A is this one, right? So B minus A intersection B is also same. So one see this one. This is A intersection B, right, sir? This is A is B. From B, if you subtract A intersection B also, we will getting the same thing. This is subtracted. So from B, this is A intersection B. If you subtract that, this one, we will get the same thing as B minus A. So these are the important things. Now observe that A union B is equal to A union B minus A. Consider probability on both sides. Probability of A union B minus A. By axiom of additivity, A and B minus, since A comma B minus A are exclusive events, exclusive implies that by axiom of additivity, only we can apply they are disjoint only. Axiom of additivity. What can we write when they are disjoint? That can be written as probability of A plus probability of B minus A. I told that previously B minus A is nothing but B minus of A intersection B. What is the remainder? I told that when one set is subset of other, so probability of the difference is equal to P of B minus P of A. One see this one. Clearly A intersection B is subset of probability of B minus probability of A intersection B, because by the remainder. So once observe that this is A intersection B, right? A intersection B is subset of B, right? Subset of B, subset of A also. When by the remainder 2, we can write this one as probability of B minus probability of A intersection. Therefore, P of A union B is equal to P of A plus P of B minus P of A intersection B. Next one is the second one, define conditional probability. We have to remember the conditional probability, no issues. We have to conditional probability. If A and B are any two events of a sample space yes, and P of B not equal to 0, the probability of A given the event B has occurred, given the event B has occurred is called the conditional probability. Mean that after B has occurred, we have to find the probability of A is called the conditional probability of A given B and is denoted by and is denoted by probability of A given B, and is defined as probability of A given B is equal to probability of A intersection B by probability of B. Now this is the definition of conditional probability. Multiplication theorem. Multiplication theorem is a cross multiplication of conditional probability statement. Statement is if A and B are any two events of a random experiment where P of A not equal to 0 and P of B not equal to 0, then probability of A intersection B is equal to P of A into P of B given A, or else this can also be written as probability of B into probability of A given B. Proof is very easy. If you know the definition of conditional probability, the cross multiplication is the multiplication theorem. Let S be the sample space. Let S be the sample space of the random experiment. Given A and B are A comma B are two events such that P of A not equal to 0 comma P of B not equal to 0. By the definition of conditional probability, what is that? Probability of B given A is equal to probability of B intersection A by probability of A. So cross multiplication, sir. Probability of B intersection A is equal to probability of A into probability of B given A. Similarly, we can prove that probability of A intersection B is equal to P of B into P of A given B. Done. Third theorem is Bayes theorem. Statement. Suppose A1, A2 and so on A and R n mutually exclusive and exhaustive events of a random experiment with the sample space S. Such that P of A not equal to 0 for any event A. Such that P of AK given A is equal to P of AK into P of A given AK by summation I is equal to 1 to n P of AI into P of A given A. Yeah. So once let us write what is there, sir. We should be more careful about that. Proof. Let us write what is given. Given P of A not equal to 0. For I is equal to 1, 2, 3, P of A, P of AI not equal to 0. P of A not equal to 0. For I is equal to 1, 2, 3 and so on. A1, A2, A3 and so on An are mutually exclusive and exhaustive events. Mutually exclusive and exhaustive events. Let us understand that what is mutually exclusive and exhaustive. Mutually exclusive means that AI intersection Aj is equal to empty. There is no intersection for I not equal to 0. What is exhaustive? Exhaustive means that A1 union, A2 union and so on union An is equal to sample space. These are the most important things. So I want to try to do this question. So I want to draw the diagram once. See this one. These are A1, A2, A3 and so on An. Suppose A is an event. So once observe that A1, A2 and so on An are mutually exclusive. So this is the event A. Once observe that this is the A intersection A1, right? This is A intersection A2. This is A intersection A3. These are also mutually exclusive, right? These are also mutually exclusive. Once observe that this is sample space S, right? So we have A is equal to S intersection S or A intersection S or S intersection A. So reasoning. Here one thing is that A1, A2 and so on mutually exclusive. Clearly I am writing. Clearly A1 intersection A, A2 intersection A and so on An intersection A are also mutually exclusive. Mutually exclusive. We have A intersection A is equal to S intersection A, right? That implies that probability of A is equal to probability of A intersection S. A intersection is nothing but S intersection A. What is S, sir? From this one, S is equal to union of all this. What is that? Union, intersection, right? Intersection A1 union, A2 union and so on union An. So this can be distributed to all these terms. So probability of A intersection A1 union probability of A intersection A2. This is equal to union A intersection A2 union A intersection A3 union and so on union A intersection An. So once observe, these are all mutually exclusive events. By axiom of additivity, what can you write? That this is probability of A intersection A1 plus probability of A intersection A2 plus and so on plus probability of A intersection An. Once observe that. Now we are going to use multiplication theorem, sir. By multiplication theorem says that probability of A intersection B is equal to, what is that? Probability of A intersection B is equal to this one, P of A into P of B given A. So P of A intersection B is equal to P of A1 into P of A given A1, right? This is P of A2 into P of A given A2, right? Plus and so on, plus P of AN into P of A given AN by multiplication there. So this can be written as summation P of AI into P of A given AI. Keep it like that. I is equal to 1 to n. This is equal to P of A. Do remember. This is P of A. Keep it like that. We need this one. Don't forget that what we need to show. We need to show P of A given P of AK given A, right? So consider. Now by using a conditional probability theorem, what is this one? P of AK intersection A by P of A, conditional probability definition. So I am writing this one as P of AK into P of A given AK. What is this formula? Multiplication theorem. Multiplication theorem by P of A. What is P of A? Let it be 1, sir. So P of AK, P of A given AK, what is P of A? Summation I is equal to 1 to n P of AI into P of A given AI from 1. So hence the base theorem is proved.